Hello and welcome back to another episode of Math with Son. Today we're going to be continuing momentum, but it's going to kind of be a detour because we're talking about center of mass. And the center of mass is essentially where things are balanced. Like where it would balance and not teeter over from one side to the other, like I did with that ruler barely. And if all the forces of gravity are acting on a rod like so, if you could balance it at one particular point, that gravitational force center, that would be the center of mass. All right, and it can be used with momentum because if you use the center of mass within momentum in a defined system, it would equal zero via the conservation of momentum, and so on and so forth. It has a lot of other benefits in other areas of physics as well. So, calculating the center of mass is dependent on where all the masses are. All right, but we'll write the formula down first. In general, to find the center of mass, the distance typically thought of as from the left, the x centimeters or meters or whatever from the left would equal the mass of 1 times like x1 plus the mass of 2 times x2 plus the mass of 3 times x3 divided by the mass of 1 plus the mass of 2, so on and so forth. So essentially it is the sum of all the x masses divided by the sum of all the x distances. That would be how far away it is from the left to the center of mass. Okay? So, with that in mind, why that makes sense, how that makes sense, and so on and so forth is related to this idea. Like, let's say we had a teeter-totter here, and you got a bar. And let's put a really heavy weight on this side. Really heavy weight of 100 kilograms. If we put a 50 kilogram weight right here, that's not going to be enough. If we put another 50 kilogram weight right here, it would also not be enough because it's closer to the center of mass. The further away you get from something, the more torque and the more like actual impact it will have, and it's directly proportional to how far away you are from the center of mass. So if these two 50s don't equal that 100 because of leverage, you would need maybe another 25 here, or if you did a different example, if you took the center of mass and you had 100 over here, if you went twice the distance, then you would only need 50, okay? That one tiny bit, because of the way it is working with the center of mass, will be dictated by how far away you are from the center. All right. If you have to deal with x and y directions, the x center of mass would be what we just did, m1 x1 plus m2 x2, and this goes on forever. And then you would divide by however many you have, m1, m2, dot, 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 dot. If you wanted to find the y center of mass, it'd be the same thing. It'd be m1 times y1 plus m2 times y2, dot, 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 if you had three centers. And then this would be m1 plus m2, and it keeps going on forever as well. So you deal with them separately. That's the main part here. You deal with the x values different than the y values. You deal with the x values to find the x center of mass. You deal with the y values to find the y value center of mass. And then you put them together in a coordinate plane to find out the center of mass is probably somewhere in between them. All right? Depending on how heavy it is, it might be a little more lopsided. If mass 2 was a little heavier, it would be lopsided and moved and shift it towards that spot. Okay? So, got a few examples for you. This first one's not really an example, but more of an enlightening thing. If you have a firework that reaches the top of its parabolic trajectory and explodes, firework going to the top, it explodes. It's a firework. All right? And then when it explodes at the top of that trajectory, what happens to the center of mass of the systems of the shell fragments? Well, here, all the shell fragments are going to be falling in whatever way they decided to explode, but the center of mass will continue its current trajectory, not trajectory, okay? Since the explosion only involved internal forces, no external forces. If you had an external force, then you can move the center of mass. If you decided to, while in the air, push it or if we dealt with friction or something else. But as long as there is no external force, that center of mass will continue to follow its motion that it did before, which is why we connect this with momentum and collisions. All right, we got 3 people standing, not doing their physics homework as shown below. Find the distance of the center of mass of the 3-person system from the leftmost person. So I'm going to deal with it from the leftmost person. So we're going to be going from the left. So whatever we get for this distance, we'll be having to move this way. All right, so we have 70 all the way to the left. We have 82, which is more, way to the right. And then we have the 60 that's kind of in the middle. It might be that 60 might be a little bit to the left or a little bit to the right. Let's use logic first. 70 is less than 82. 60 is going to have to be on the left side of the center of mass. I would expect the center of mass to be somewhere around here because some of the 60, but not a lot of the 60, would need to help this 70 kilogram person out. Otherwise, the 80 kilogram person would teeter this totter. Think of a teeter-totter, like a seesaw. All right, so using our formula, we are going to have to take x1 times the mass of the first person. So this would be 70 times x1. Well, x1, that distance from the left would be 0. So 70 kilograms times 0 plus the weight of the second person, which is 60, times their distance from the left, which is 4, plus 82 times their distance, which is 10. And we would need to divide that by the mass of all 3, which would be 70 plus 60 plus 82. And if we do this math, you end up with 70 times 0 plus 60 times 4 plus 82 times 10, all divided by all that stuff. You end up with the x center of mass of 5 meters from the left. From the left, which makes sense not because it's halfway between 6 and 4. That's just a coincidence. It makes sense because where I predicted 5 meters from the left is about where that would need to be to counteract the full 82 that we had here. Okay, so it counteracts that. It's not going to have the 60 being far off to the left. It's not going to involve that. We need a lot of this 82 to be enacted here for it to be balanced. All right, that's going to do it for this one. I think it also wraps up the momentum unit. We're going to be doing rotations next, and I would look forward to seeing you then. Bye now, folks.